Welcome to the third talk of this session. It's my great honor to introduce the next speaker, Professor Mikhail Kapranov. He's a world-renowned expert in algebraic geometry, category theory, representation theory, and mathematical physics. And he's going to talk on perverse sheaves, both algebras and induction sheaves. So let's join me in welcoming Professor Kapranov.
Thank you very much, and I should start by thanking the organizers for putting together this great congress, for recognizing our work, and for providing an opportunity to present it. So my talk will be about the concept of perverse sheaves and rather some elementary aspects of this theory and some attempt to understand the deeper structure of this concept. So perverse sheaves by now are used so much in mathematics, like in different areas. Like for instance, in the previous talk of Yuki Nobutoda, the perverse sheaves were everywhere. So by now, people sort of assume that if something interesting happened, there should be a perverse sheaf behind it. But it's interesting just to think, why should this be so? Why perverse sheaves are such a thing in the first place? So let me start discussing this naive question a little bit. So what I wanted to say is that, again, it is not something new, but the perverse sheaves, their point is that they are self-dual objects. So originally, perverse sheaves were introduced in the context of intersection homology, to try to construct homology theory for singular varieties, which would satisfy Poincare duality. So naively, Poincare duality sort of identifies some homology with some cohomology. And more conceptual, and intersection homology is some particular theory which coincides with one or the other, depending on the singular, whether variety is smooth. So if you look at coefficients, then cohomology have sheaves as their coefficients. So dualizing, we can have a concept of co-sheaves, which is used a little less frequently, but is dual to the concept of sheaves. And perverse sheaves are somehow in between. So more formally, one can say that sheaves and co-sheaves and perverse sheaves, they are embedded into a bigger triangulated category, the derived category of all sheaves. And Poincare duality, or rather Verdier duality, it interchanges sheaves and co-sheaves and preserves perverse sheaves. So intersection homology corresponds to some particular perverse sheaf, which is self-dual under this duality. And on the more naive level of set and vector spaces rather than categories, one can compare this with duality between functions and volume forms. So volume forms you can integrate and get a number. Functions you cannot integrate, but you can pair with volume forms. But in sort of finer aspects of mathematics, especially those related to quantum mechanics, it is the concept of half forms, square root of volume forms, which appeared. And again, we had exactly this concept in the name of orientation in the previous talk. So from a naive point of view, the importance of half forms is that they pair with themselves. And we can take one half form and another half form, multiply, get a volume form, and that's an L2 space. So in all aspects of quantum mechanics, various objects are half forms or half densities, for instance, in quasi-classical approximation. So perverse sheaves, one can be said that they are conceptual analogs of half forms. With this understanding of them being between sheaves and co-sheaves, one can somehow understand their connections with other objects. So now let me discuss concept of perverse sheaves more formally. So they are defined for stratified space or stratified complex manifolds. So let me just draw a picture of a stratified space here. It would be one of the pictures I draw. So it's a complex manifold X, which is stratified into union of strata X alpha, which are smooth. But the closures may be singular. So a typical example would be you have plane C2. Here you have a semi-cubic parabola, y squared equals x cubed. So it's, of course, singular. But we consider the stratum being everything outside of this, and the stratum consisting of 0. So this has 3 strata. So for such a stratified space, we can consider constructible complexes. Constructible means complexes whose cohomology sheaves are locally constant on each stratum. And moreover, there are conditions that how this cohomology sheaves behave. So the first condition, this is called the perverse T structure, that the ith cohomology sheaf is supported on dimension less or equal than minus I. It means that only negative cohomology are present. So when we approach H0, it kind of dies out. So for this thing, it would be the zeroth cohomology sheaf will be only at this point, minus first cohomology sheaf can sit on this, and minus second cohomology sheaf can be everywhere. So it sort of kind of dies out like a smile on the cat, on the proverbial cat. And the dual condition is that they die out, but not too fast. So I won't write the precise condition. It is dual, again, in various senses. Together, they form, so those conditions form the so-called perverse, middle perversity structure. So this normalization that we put this thing in degree 0, and in fact, the perversity structure itself, it corresponds to the idea known since Lefschetz that most interesting homology of an algebraic variety happens in the middle dimension. And everything sort of revolves around the middle dimension. If we renormalize, if we shift so that the middle dimension in degree 0, we sort of inevitably are led to the concept of perverse sheaves. One can put it like this. So, and of course, one known reason for interest in such objects is that by Riemann-Hilbert correspondence, they correspond to holonomic systems of linear partial differential equations. In fact, if you consider holonomic regular, then it's a one-to-one correspondence. In general, it is not one-to-one. So what's important is that these objects form an abelian category. So that's why they are called sheaves in the first place. And perverse because, well, it's not really sheaves. So it's an abelian category. Moreover, this abelian category carries a perfect duality. Every perverse sheaf, to every perverse sheaf, we can associate its dual, and the double dual will be F itself. So in this sense, so if you sort of go to the previous slide, so this red arrow represents Verdier duality. So this is an abelian category of finitistic nature. It has finite length and co-length, means or how you say it. It is Noetherian and Artinian. So in a typical such category would be the category of finite dimensional representation of an associative algebra, or of a quiver with relation. Again, quite familiar concepts. And it's interesting to look for such realizations. For example, consider the most standard, sort of simplest example. We have a disk. Suppose not even this example, but even more elementary example. We consider a disk with a point 0. So there are 2 strata, and there are 2 I can mention two descriptions of this. One is through now classical phi-psi description, when phi is the space of vanishing cycles, psi is the space of nearby cycles, and the condition is that identity minus decomposition is invertible. This invertible map is the monodromy of the perverse sheaf. For example, in this case, on the psi, it is a psi is the space of is the fiber at the generic point of the disk, and this transformation is the monodromy. And there is another description which we found with Vadim Shechtman. It can be called the Dirac description. It has three terms, so three vector spaces and maps like this in both directions, satisfying two conditions. The first, if you go from E minus to E0 and back to E minus, you get identity. Or similarly for E plus to identity. And if you go through, that is invertible. So in fact, those descriptions are analogous to what's known in, again, in quantum mechanics as abstract scattering theory. So in the old days, when people studied potential scattering, so there was a formalism of sort of scattering process, and then we can say that E minus corresponds to the incoming space of waves at the negatively infinite time. E plus is the outgoing space, so at the time plus infinity. And there is some interaction happening in E0, and if you go through, so this is some kind of scattering matrix. And this is not a completely meaningless analogy. So in the classical theory, the scattering matrix is unitary, which means they're going this way, and this way is, there is some duality between them. But in this situation, it is kind of similar. One can look at this from this point of view. And once you get into this mode, then even this can be seen as a scattering theory interpretation. When you, instead of going from negative time to positive time, you think about stationary scattering process. When you have something like a standing wave, and on the, say you have a scattering over a radially symmetric potential, and so they're going back and forth, corresponds to the scattering process. So I return to this point of view a little later, but what I want to emphasize here, that those diagrams are manifestly self-dual, and they should be self-dual in a good description, because the category itself is self-dual. But as I said, self-dual structures are very important. If something is not self-dual, then you can dualize it and get a new structure. And when something is self-dual, you have a feeling of perfection. It cannot be modified in such a trivial way. So let's look at other self-dual structures. So probably the most familiar or the most famous self-dual structure is that of a Hopf algebra or a bi-algebra. In an algebra, we have a multiplication from A tensor A to A. In the bi-algebra, so dually we can dualize the concept and say there is a co-algebra. We have a co-multiplication from A to A tensor A and dualize the axioms. But it was understood a long time ago that the combined structure is very important when we have both multiplication and co-multiplication. And we need to specify how they interact. So the most general setting for a Hopf algebra is that of a braided monoidal category. So V is a category. I assume it's linear over some field. I don't write the field here. So the tensor product monoidal structure, I assume it is strictly associative. This can be achieved when necessary. There is a unit object, and R is the braiding or the R matrix. So in fact, if you try to write axioms for bi-algebra or a Hopf algebra, we absolutely need this braiding. And I want to look at a particular case when the algebra is graded. So it's a direct sum of graded components. So suppose in our category V, we have direct sums, right? A graded component, and it sort of is connected and co-connected, as they say. So A0 is the unit object, and I have here concept by unit, which means that there's a unit and a co-unit. So if we now kind of expand the axioms of a Hopf algebra in this situation, then we obtain a very interesting, algebraically, very interesting straightening rule. Suppose we have several components, we multiply them, and then co-multiply them into some other way. So here alpha 1 and alpha k must sum to n. And beta 1 and beta l also must sum to l. So there, as they say, order partition of the, to n of the same number. So if we do this, then it will give us several summands in which will be labeled by what we call contingency matrices. It's a matrices of integers, m11, m1l, mk1, mkl, of non-negative integers, which row sums are the alphas, and column sums are the betas, and we assume that there are no row and columns consisting entirely of zeros. So what happens here? We have tensor product A alpha 1 to A alpha k, and A alpha 1 is split into this tensor product. A alpha 2 is split into this tensor product in the next row. A alpha k split into this tensor product. So, and then, so if you think of this naively, we combine them vertically and go into betas. But there is a little subtlety here, because strictly speaking, the multiplication in the braided category is not commutative. So we need to pass, strictly speaking, this tensor product would map into the product when we're doing first the first row, then the second row, then the last row, the horizontal reading of this matrix. And in order to go here, we need to start with the vertical reading, with the vertical like this, and like this, and like this. And then we should use the R matrix, the braiding, to pass from the horizontal reading to vertical reading. So in a sense, this two-dimensional array can be seen as a two-dimensional tensor product in a braided category. This is the point of view of Deligne, who famously proposed that to understand braiding in such a way that there are tensor product associated with every positions of objects in a two-dimensional plane. This, of course, is a particular case of E2 structures in general. So here they are positioned in the plane in such a way that sort of they are in the lattice. So what's interesting that we have, by doing just this simple algebra, we arrive sort of at the concept which has been originally introduced in statistics as contingency matrices. So we consider matrices whose row sums is one partition of n, and column sums give another partition of n. So this appears when we study joint distribution of two set of random variables or two factors. For example, we can say how the number of cigarettes you smoke coincides with the age when you die. So you put samples. Here would be the number of cigarettes you smoke, and here you have how long do you live. And for every person you sample, you put a one in the corresponding position, and then you see if there is some correlation close to this. So then there is a probabilistic reason that one thing correlates with the other. So already interesting that such elementary observation leads to this concept which appeared for a different reason. So this is another example of a self-dual structure. Now let me consider a third example of a self-dual structure, corresponding to induction and restriction formalism. And also I have here Eisenstein series and constant term. Yeah. So let's consider the situation. I don't specify all the details. Consider the situation of a reductive split group of the simplest case over Z. So it has the corresponding Lie algebra, Cartan subalgebra, roots, simple roots, Weyl groups, and so on. So, and we have a parabolic subgroup in this, say, standard parabolic subgroup, and it projects to its Levy quotient. And in such cases, we have, as I say, in various contexts, we have the induction and restriction factors. What do I mean by context? Well, we can consider groups over a finite field. We can consider groups of points over real numbers, of a group of points over p-adic numbers, or adelic automorphic representations. In each such case, we have the concept of induced representation. So we have a representation of M, we lift it to P, and then we induce to G. That's called parabolic induction. And dually, if we have a representation of G, we have the space of invariance of the unipotent subgroup, which I don't include. And this space of invariance of the unipotent subgroup is a model over the Levy. It's an adjoint factor. So, of course, if we combine one induction and do restriction to another subgroup, so that is given by the classical theorem of Mackey, which calculates this in terms of double cosets. But what's interesting is a refinement of this observation in the situation of automorphic forms. When I speak automorphic context, that means that I consider a group and a discrete subgroup. Or more formally, I consider situation of an algebraic curve over a finite field, or an arithmetic curve, which is a spectrum of a number ring. In such a situation, the space of unramified automorphic forms is a particular subspace in the principal series representations of the representation of the corresponding group. And there are maps known as Eisenstein series construction and constant term construction in this case, which interchange go from automorphic forms on the Levy subgroup to automorphic forms on the group. And here, again, the analogy with scattering has been noticed for a long time. So one automorphic context is that of, maybe I'll write it here, the automorphic concept is of the upper half plane of SL2Z. So it's usually written like this, or we can say it's like this, and there is a cusp. So the Eisenstein series in this case is an analog of the standing wave. So a solution of certain Laplace equation or automorphic wave equation correspond to standing wave. Maybe I'll write it here. The Eisenstein series so in the old days, this analogy caused a lot of excitement. Analogies between theory of automorphic forms and scattering theory. That was at the origin of the program of Gelfand on automorphic forms in the 60s. So what I want to point out here, that in this enormous theory, I just sketched some superficial feature, but there is a standard formula by Langlands, which says what happens if you have two standard parabolic subgroups, and we first do Eisenstein series, and then constant term to another one. It is a refinement of the Mackey theorem, but it will be actual sum over the double cosets of summands corresponding to three things. There are, first of all, constant term and Eisenstein series are interchanged, the order. And second, in between, there is so-called intertwiner, parabolic intertwiner between principal series representations. And this accounts for appearance of zeta functions in the formula for the constant term. So this circle product P circle Q is the so-called Tits product. I will explain it a little later. So it's you have two, let's say, semi-standard parabolics. After you act by the Weil group, it will be semi-standard parabolics. And this will be certain parabolic which refines P. And this will be the intertwine. So will be this type of formula. Now, if our group is GLN, then parabolic subgroups in GLN are labeled by the same thing as here, by this type of partitions. We have alpha 1, alpha k. We have block triangular matrices with blocks of size alpha 1, alpha k. This way. Yeah, and we get exactly the same formula. So roughly, there will be some factors here, but the structure of the formula will be exactly the same as in graded Hopf algebra. This is because the space of contingency matrices can also be realized as the set of double cosets of symmetry group Sn modulo S alpha, which is product of S alpha I, and on the other hand is S beta, is a product of S beta j. So in this relation between properties of Eisenstein series / constant terms for automorphic form for GLN and Hopf algebra structures, in general, it is a manifestation of the construction known as the whole algebra of an abelian category. In this case, the abelian category will be the, or exact category, the exact category will be the category of vector bundles, say on an algebraic curve, and multiplication and co-multiplication are given by extensions. So this is actually a remarkable correspondence. This thing matches this thing. Matches this thing. So now let me discuss one method we used to analyze perverse sheaves. This method is based on, it's not purely algebra geometric. It's based on viewing the complex number, a complex number as consisting of a real and imaginary part. If you have a complex manifold X, we want to choose what we call a totally real skeleton. It's a subvariety of middle dimension, real middle dimension, whose complexification of tangent space is, whose tangent space has no complex parts, so to say. So that can be roughly said, sort of metaphorically, that a totally real skeleton wants to be Lagrangian. So in this case, it sort of connects with the Lagrangian point of view in point of view of Fukaya categories and symplectic geometry. Except here, we don't use the symplectic geometry, that is scalar structure, and just use complex geometry. But the property of this, of totally real manifolds are in many respects similar to the properties of Lagrangian manifolds. For example, if you have a complex vector space, and we consider the Grassmannian consisting of all totally real subspaces, it is homotopy equivalent to the Lagrangian Grassmannian of the corresponding symplectic space. So we use this, roughly saying it's a total real skeleton, and what happens quite often that cohomology with support in this Lagrangian skeleton vanish in degrees other than 0. This actually the earliest, and although it wasn't formulated like this, a statement like this is due to Sato to Mikio Sato in his theory of hyperfunctions. In Sato's theory, he considered, instead of a perverse sheaf, he considered the sheaf of holomorphic functions on Cn, and for lambda to be Rn. So in this case, there is only one cohomology in degree n, and this cohomology sheaf is the famous sheaf of hyperfunctions of Sato, which is a different algebraic approach to the concept of distributions of generalized functions. So the situation we considered with Vadim Shechtman is also rather simple. We consider the complex vector space. The Lagrangian skeleton, the totally real skeleton, is a real space, and S is given by family of hyperplanes with real equations. So if we think of a perverse sheaf as the complex of solutions of a D model, then this would be the sheaf of solutions in hyperfunctions, set of distribution solutions, so to say, very natural. So what happens if this vanishing theorem holds, that the remaining functor from perverse sheaves to ordinary sheaves is exact? And that's cool, because whenever we want to have a description by quivers, then every vector space in the quiver should be an exact functor of the perverse sheaf. So here we have, by considering stocks of this new sheaf, we get many vector spaces. So this suggests naturally to take those stocks as vector spaces of the quiver. So what will happen in this case? That if we do this, we'll have a sheaf on Rn. It will be constructible with respect to this stratification by faces of the arrangement. So faces, again, sort of locally closed thing, like a point is a face, this open half line is a face, and the open sector is a face. So as any constructible sheaf, it can give stocks and generalization map from a smaller stratum to a bigger stratum. So already we get such a diagram, which is an exact functor of a sheaf. And using a Verdier duality, we can apply, I'll skip this part, we get the maps in the opposite direction. And they're transitive because it's representation of the poset. So the situation we considered I considered in the very beginning, with E0, E plus, and the minus, it was this. So we consider C, we consider R, so E0 will be stock here, sorry, E minus will be stock here, E0 will be stock here, E plus will be stock here. So this a priori, the sheaf will give this thing, and the by duality will get the other thing. So in this way, we get a bunch of vector spaces and maps between them. We get a quiver. So let me formulate this statement. That is our result, that the category of perverse sheaves constructible with respect to this stratification. So maybe I haven't said that properly. The stratification is given by family of hyperplanes. So the strata are what they call, each sort of, there would be some called flats of the arrangement, and each flat is a subspace, and we consider the subspace minus all the next level subspaces. So we have those diagrams. So just each of them, let me call them induction and restriction, just to emphasize the analogy. Each of those are transitive. They satisfy the idempotence. Is the same thing that I said in the beginning. Here we go from the smaller to the larger and back to the smaller. It is identity. And this gives, actually, if we do this, gives some maps which do not respect the order. If you have A and B, any cell, then if we get to take any smaller cell, sort of lies in the closure of A and B, for example, 0, then we will have this composition that will be independent of how small you take this. And if A is contained in less than B, then we get res, and if A is greater than B, we get int. So the second condition is the so-called collinear transitivity. So if we have three faces, A, B, and C, and they contain 3 points, small a, small b, small c, such that B lies inside the straight interval from A to C, then this thing is transitive. This again generalizes transitivity for res and transitivity for int. And another property is a generalization of those invertibility of going through. We call it invertibility in wall crossing. So that's invertible if you have two cells having the same dimension and lying on the opposite side of one dimension actually lower rather than higher. This is a misprint. Of one dimension lower. This and this lie on the opposite side of this. This thing is a wall. So see, I screwed up a little. Yeah, so and this gives what we call half monodromies, or we can call them scattering matrices using metaphorical language. And this gives action of fundamental groupoids, braid groups, and so on. So this can be also seen as kind of scattering in the situation when we have incoming and outgoing waves in different chambers of this arrangement. So now with Vadim and Olivier Schiffman and Jean-Fan Yuan, we understood this as a version, as a kind of prototype of the Langlands formula. So what happens here? So first of all, I recall, I return to the concept of the Tits product. If you have two faces, say this is face A, and this is face B, that A circle B is the unique face if you go from point on A to point on B in an interval. Then the very first that we hit after we depart, the very first face, is uniquely defined. And this is A circle B. And this circle is an associative operation, but it's not commutative. And B circle A is not the same as A circle B. And this example, A circle B is this sector, and B circle A is this sector. But what's always true, that they are associates, which means they have the same dimension. Even for whichever A and B I start, A circle B and B circle A will have the same dimension. Moreover, they will have the same linear span. So if we take their linear span, that in this linear span there will be chambers. So passing from one to the other, we should just cross a few walls and get using some element of the braid groupoid. So in this case, the collinearity condition, so we consider this at the same time as this, gives a version of the Langlands formula, but with one summand. There's one summand. There is no summation over the braid group. It's the same pattern, and there is a braiding in between. Maybe I should say one more thing about relation of this Tits product with horizontal and vertical reading of the two-dimensional product of Hopf algebras. Return here. So here we have this reading versus this reading. So this actually corresponds to two Tits products here. Yeah, the two Tits product. Maybe I just say once more here on the board. That if I have, we consider Rn, and we consider root arrangement xi equals xj. So we have something like this. So and face correspond to a partition I1, sort of ordered partitions of sets I1, Ik. So disjoint union I equals 1. So we have one such partition and another such partition. Suppose we have J1, JL. If we have two partitions, two set theoretic partitions, then we have I small I intersected J small j. Let me call it Mij. That's a contingency matrix. So if this face is A and this face is B, then A tensor B is an A circle B is a vertical reading. And B circle A is horizontal. So this seemingly very algebraic, sort of very naive concept of vertical versus horizontal corresponds exactly to this structure. And we call this the proto-Langlands formula. It has consequences for perverse sheaves now on the quotient. So we start with the Cartan subalgebra complex stratified by root arrangements, something like this, by the root arrangement, something like this. And it has the induced stratification on the quotient, H mod W. So H mod W is a smooth space, but the stratification, the closures of strata are not smooth. Because in the simplest example, when we have a general linear group, the W the symmetric group, the quotient is the symmetric product of the complex line. It is the space of polynomials by elementary theorem, and stratification goes by root multiplicities. So it will be exactly something like this. This corresponds to polynomials of degree 3. So generic stratum is polynomials with 3 distinct roots. So the next subgeneric stratum, 1 root of multiplicity 2, and the lowest stratum, 3 roots coincide. So it's quite non-trivial system of singular algebraic variety. So by the previous theorem, if you want to consider perverse sheaves on the Cartan subalgebra itself, it is representations of certain quiver. Or we can say it's category of models over the corresponding algebra, or functors from certain category. We consider the category whose objects are faces, morphisms are generated by those int and res, subject to relations. Then to say that we have a diagram of this property is the same as to say that we have a functor from this category. And alternatively, we can say that's model over this algebra, which is direct sum of Hopf's between all objects of the category. So our theorem with Olivier Schichtmann, with Vadim and Olivier Schichtmann and Jafan Yuan is that the category of perverse sheaves on H mod W, with respect to this stratification, is the category of models over the invariant subalgebra. So the group, the W, the Weil group acts on this whole picture, it acts on this algebra, and inside there is subalgebra of invariance. So we are saying that the category of perverse sheaves on the quotient is the same as the category of models over the invariant algebra. And here are two interesting remarks. So first of all, the natural elements, sort of generators, so to say, of the invariant algebra are certain sums or averages of the elements of the original one. How to construct an element of the invariant subalgebra? We take something and move it by the group and consider the average. So if you do those averages, then this formula for individual things will give, on average, the Langlands type formula with this type of sum. So there is a match in this respect. And another interesting aspect here is the match between invariance in commutative and non-commutative geometry. So space H mod W is the spectrum of the ring of invariance. So coherent sheaves or quasi-coherent sheaves in H mod W are models over this algebra of invariance. So perverse sheaves on H were models over algebra A, and perverse sheaves on H mod W are models over algebra of invariance. This is kind of very pleasant formalism. How much time I have? Plenty of time. Oh, what I'm doing? Oh, I did something with the computer. Now it's how. I just hit some key, and so maybe it should be very simple. But oh, thank you. Yeah, it's just so bad with computers, right? Yeah. Now, so let's return to the concept of Hopf algebras to connect everything together. All the self-null structures we can think of, or at least what we could think of to connect, we can connect. Let's consider again this concept of graded Hopf algebras. So when we do this, we first of all notice that it's not necessary to consider direct sums. What we need are such partial multiplications and co-multiplications, satisfying the properties which we can extract. And this formula with contingency matrices is an example of such a formula. So we can consider such things in any braided monoidal category. So once we do this, we can consider the universal such object. Consider the universal category B, which is generated by formal symbols AN, standing for indeterminate components of an algebra, and the morphism between them like this, subject to axioms. So the advantage of such things would be to say that a braided functor from this category B to any braided category V is the same as a graded Hopf algebra. If we look more carefully, then the objects of this B would be simply, we say it's generated. Generated as what? Generated as a braided category. So it's a little bit subtle concept. So objects are generated. So objects are all tensor products. And how morphisms are generated? Basically anything we can compose, subject to those locally defined relations. But anyway, objects are like this. They correspond to ordered partitions. This ordered partition has order, partitions of what? And in such category, because you see this thing is additive here, that if the subcategory spanned by a n, boldface n of given cardinality, they don't talk to each other. They are blocks. The home between them are zero. But of course, they are not tensor categories. So our theorem is that if we have a not necessarily braided category, or abelian category, for example, of category of vector spaces, but not, or models or over something, then the category of V-valued perverse sheaves here is the same as the category of functors from this block Bn to V. Now, if V is some category not realized as a category of vector spaces, then one can still talk about V-valued perverse sheaves by dealing with things combinatorially, by saying, okay, what's a perverse sheaf? A perverse sheaf is a complex of sheaves. Complex of sheaves cellular to some cell decomposition of sim and C, and a cellular sheaf is a combinatorial datum. So we have a complex of cellular sheaves, and in this way we can speak about perverse sheaves with value in any abelian category. So that's interesting because we started with the idea of a Hopf algebra, and somehow we pretended for a while that there is a multiplication and co-multiplication. We extracted the morphisms and then forgot about multiplicativity. This is somehow similar to the old-fashioned symbolic method of invariant theory. We work with tensors, but we pretend the tensors are decomposable tensors and do something for them. But then we sort of extend our considerations to things which are not multiplicative, not decomposable. So this is an interesting generalization. So such individual perverse sheaf, of course, is not a Hopf algebra, because it can even be defined in something where Hopf algebra doesn't make sense. But if you want to consider situation with Hopf algebras, if the category is braided, then we can consider braided functors. And the braided functor from the full B, it can be restricted to each individual Bn. If you restrict to individual Bn, we get a sheaf on the n symmetric product. So, and then it is not from the previous thing, it's not hard to see that graded Hopf algebras in this way are identified with factorizing systems of perverse sheaves. So a system consisting of one perverse sheaf on each symmetric product, and have factorization properties like it's the simplest. 5 minutes, yes. It is exactly what I more or less want to say. Yes, which are factorizing with respect to some decomposition of symmetric product of a disjoint union, and this completes sort of the most neat formulation of the results. We're going back to Finkelberg and Schaffman and to Gatesbury somehow about the corresponding between duality of E2 algebras and Cazul algebras. Now, to consider, to finish, I have, yes, fine. So method number 2, which we consider, and maybe I'll stop at this slide, is kind of dual. So first, I was talking about totally real skeleton, a sub-object. If it deals with linear space, then the sub-object is the same as a quotient object, because we consider the quotient by the subspace. For nonlinear manifolds, it's not the same. And we can consider totally real fibration is something like a Lagrangian fibration or an integrable system. And the simplest instance would be Cn projecting to Rn, or symmetric product of C compared to symmetric product of R. So, and in good cases, what happens is that a complex becomes a datum in degree 0 after we apply relative Verdier duality along this projection. So in some sense, we can say that a perverse sheaf is a sheaf in real directions and a co-sheaf in imaginary directions. And that can be analyzed. And an example of this is 3 appearances of contingency matrices. That is the first concept of contingency matrices I explained. Second, so 3 appearances are like this. First, as the Briard decomposition. Second, Hopf algebra axioms. And third is the cell decomposition of symmetric product of C. If you have a bunch of points in C, then we look at the real parts, look at their imaginary parts, and we have a contingency matrices showing up right there. And if we fix contingency matrices, we have a cell. So this particular cell decomposition, analyzing this, gives our description. So maybe I should meant to say, just was interrupted, that in this aspect there was a recent paper of Tobias Dickerhoff and Paul Wedrich who have categorified this approach. They described instead of perverse sheaves, they gave a definition of what's called perverse Schobers, which are categorical analogs of perverse sheaves in this case. And in particular, it leads to the concept of categorical analog of a Hopf algebra, which I think is very interesting. So all this point that perverse sheaves are in between sheaves and co-sheaves, they get somehow gets its interpretation from this particular point of view of, so to say, wannabe integrable systems. So probably I'll stop here. Thank you very much.
Questions?
Okay, so I have a general question. I know that you work with Gelfand and so many great mathematicians. Also, I know that you worked on abstract harmonic analysis and PDs, ODs. I know that. Can you tell me, I mean, as someone who's working on harmonic analysis, the link of applications of these topics in general related to the harmonic analysis and the PDs? Once you talked about the linear PDs, and we saw that, but I'm talking about linking to different fields and applications.
Well, one connection is the relation between Eisenstein series and quantum groups. So if you have the properties, the functional equations for Eisenstein series for GLN, they translate into quantum group type relations in the Hopf algebra, in the whole algebra. So this by itself is some connection with harmonic analysis. Yes, there is a question. So what's the question? What is the precise meaning of this? That is not clear. There is no given concept. But in this situation, one can analyze, and it leads to the answer.
Okay. And for the sheaf and co-sheaf, should I understand them as the usual definition, or?
Yes, so something in the cells. So a sheaf is something which has data from a smaller cell to a bigger cell.
Right.
A co-sheaf is something which has maps from a bigger cell to a smaller cell. And you want to have some compatibility. If you play with this, then, yeah.
And are those restriction and induction factor you mentioned in the?
Yes, this is a kind of that thing, yes.
Okay. And what gives you the intuition, the difference between real and imaginary, like that difference?
Well, real and imaginary corresponds along the fibers, sort of along the base or along the fibers of the vibration.
Which one is the base? The real base?
No, if you consider this, then this is the base. Yeah. In such simple examples, it's easy to take either as the base. Yeah. So this is the base. This is kind of vibration. Yeah.
All right. Thank you.